All right, so let's continue onward. So now from our previous example, we went through and we filled an array with structures, which was candy. So now let's make an array of arrays. Now in C, strings are basically arrays of characters, and they're terminated by a special null character that just says, hey, you're at the last character, you should stop now. And that's /0. And you'll see in a second I had some arrays that didn't have enough room for the 0, so I just put a slash. Anyhow, so we're going to make a pointer to pointers again. So we have char pointer pointer. And so we're, of course, saving enough space again for, for length number of char pointers. So let's go ahead and put the first string in here. So now, and you can do this in C. This basically makes an array for us and then terminates it with the null symbol. So now this pointer is pointing at this array here. So, and this pointer is pointing to the first element of the array. If it had its own name, that's basically what this would be, right? So it's pointing to G. So if we did this pointer plus 1, we'd be pointing to O. And if we did this pointer plus 2, we'd be pointing to I, and so on and so forth, until we got to this null terminating symbol. That's kind of how you use the null terminating symbol too. You iterate through a string until you get to it, and then when you get to it, you say, oh, I'm there, stop. So we can put the next one in, and you can see for each of these pointers, it's going to point to its own array. And you could go through a more lengthy process of creating this. I'm just using this kind of shortcut for literals to just go ahead and put them here. So, and here's a longer one, and it's, again, all of these are going to be terminated, so you could iterate through each of these. So if we were going to go through and say we were looking for how many occurrences of the letter O there was, we would start with words, and we'd go for every element of words, we'd go through, and then we go for every element here in word sub 0, we're going to go through and check for an O. Oh, we found one, and we're done. Then we go to the next word, and we go, oh, here's another O. And then we go to the next element. And then for each of these, we go through until we find an O. Oh, here's an O, etc., etc. So essentially what you sort of end up doing is kind of like a double for loop, usually, whenever you have an array of arrays. So this is what we call a ragged array. The reason being that each of these arrays, word sub 0, word sub 1, word sub 2, they're all different lengths. So there's not like any sort of there's not any nice regularity. So you couldn't say, oh, they're all of length 3. And then you know ahead of time that you're going to go and check 3 characters and check 3 characters and check 3 characters. They're all just different lengths. I could assign a word of any length, a string of any length here. And that's why I chose for this example to go ahead and make it a C string, because they're terminated right here. So it kind of is a logical stopping point when you don't know how long each of your arrays is going to be. So that's a ragged array. An example of a non-ragged array would be, for instance, something like maybe a matrix or a table. Maybe if you had a 4x4 table. So you could represent that as an array of arrays, like essentially a 2D array. And that's kind of what this is. It's a two-dimensional array. The difference being, of course, that instead of a nice regular grid, this is a ragged array. So let's go ahead and fill in the rest. Da da da. You may recognize the song lyrics. So let's talk about memory leaks now. So we're calling stuff like alloc and calloc and that sort of thing. And every time we do that, we're grabbing a chunk of memory and we're saying, oh, this cannot be used by any other program or any other part of my program, right? And let's say, for instance, that you had a big, huge program and it was taking up, it had lots of little chunks of data that it was using. And when you're finished with that data, but maybe the program's not finished, maybe a section of the program is finished, but you don't free that data and say, oh, it's available for use again, that is basically a memory leak. And of course, you can have other issues too that arise. You could free up data too soon, and maybe there's other parts of your program that still need that data. So you go ahead and free it up, and then you have a pointer to this now freed data, and you try and access it, and you get some kind of weird error. And maybe C won't explicitly throw an error at you. Maybe you'll just get very weird data. So you have to be very careful when you free memory to make sure that you are, in fact, 100% finished with it. But the other side of the coin, what if you don't free it up at all? Then you'd end up with this memory leak, and you might potentially end up using way more memory than you should. So it's always good. It's always a good goal to try and have zero memory leaks in any C program, especially a large one. Some places to look are, if you have something that's going off and doing its own thing for a while, and it's really long, like a for loop that's maybe allocating stuff. And when you're finished with your allocations, you exit after you've processed your data and you don't free anything. That's probably a likely candidate for memory leak. You also have programs. Valgrind is a really great program. It'll show you how your memory is laid out, how efficient sort of your memory layout is, and it'll also tell you, it'll help you find and spot memory leaks. So I can definitely recommend Valgrind for C programs if you have issues finding memory leaks. So anyhow, so let's go over how to properly free up some memory. So back to our candy example where we had an array of candy pointers, and each pointer points to this candy structure, right, that we've allocated. Let's say we want to free all of this memory up. We're done with candy for now. So what if, let's rewind just a little bit. So in C, you have this function that takes a pointer, and it's called free. And when it's called, whatever block of memory it points to will be freed. So it's kind of like the inverse of malloc and calloc. If you called malloc and that's how you got that block of memory, when you call free on that pointer, that block of memory will be returned. In theory, that's how it goes. So let's say we go ahead and we free candies, right? It'll free the block of memory associated with that malloc call that we did. Remember, we did our malloc call, and it's sort of, that's this, right? So when we call free, does it really free up everything? No, it frees up candies, and of course candies now points to null, right? But this stuff, this is still in memory, right? We allocated space for these too. But now we have a problem because we've sort of chopped off our reference to these. So we can no longer access these. That's not good. We can no longer free these ever. So this is sort of like a memory leak that is permanent until our program terminates. And when our program terminates, the operating system is intelligent enough to say, hey, the program is done. Everything it ever allocated is now free. So luckily for beginning programmers, this will not permanently screw up your system. But this is definitely a problem if you're if you think that you're freeing up all this space and you're really not. Especially, can you imagine doing this inside of some kind of really long loop, and every time through the loop you think you're freeing these, but you're not? That would be very bad. So, sort of the proper way to free something, whenever you have sort of a memory hierarchy, is to delve down deep into the memory hierarchy, at whatever the deepest part is, free that first, and then go to the next part of the memory hierarchy, free that first, and etc., until that level is completely freed out. Then you go back to whatever your previous level is and free that. So first, because we sort of have a pointer of pointers, we need to go to the deepest level and free this candy here. So we have this for loop that for each of these, it calls free on the pointer, right? So we go ahead and we call free, and then again, and again, and again, etc., until our for loop terminates, and yay, we freed up all of our candy. So now that level is done. Now that we've done that, now we can go ahead and call free on candies, and that has actually freed up all of our memory associated with that. And so it kind of works the same with arrays of arrays as well. So if you allocate memory for an array of arrays, you have to go into that array and free that first, and then etc. But let's go back to our previous example with our words and song lyrics. What would happen if we tried to go ahead and free this one right here, free going to California? What if we tried to free each of these words? So we make a for loop similar to our other example, and we go down in here and we attempt to free going. We end up with an error. I think we get a segmentation fault. This could be a fun exercise, fun in quotation marks. So this could be a fun exercise to see how the freeing will affect your program. The reason why we can't free this, though, is that have we really called malloc or calloc to reserve that chunk of memory? Well, we really haven't called malloc. We didn't get this string going. We didn't get that from malloc. This is actually just a literal, and I believe it's living on the stack. So when we try and free this, it's something that your program is just keeping track of on the stack. It's a local that your whatever local function declared this is supposed to have access to, and you're not allowed to free that. So in general, anything that's kind of local or anything that you don't explicitly call malloc or calloc on will throw sort of an error when you try and free it. This could be a little weird if, say for instance, we did our array differently. Let's say that going to California, those were all just like this, literals that were on the stack. And then maybe these two, we did malloc and calloc. Now when we go through, how do we tell which ones we're supposed to free, which ones we're not? So you sort of have to be careful how you structure your program for that reason. So that sort of covers that. And I believe we have covered pretty much as we could in half an hour. So for some additional exercises, I have some code examples available. You'll need the GCC compiler for whatever system you're on, but I have I think 4 code examples that go into some pretty good detail, and these slides are also going to be included. So you can go ahead and download the link in the description of the video. If you have any questions or if there's any inaccuracies in the presentation, go ahead and give me some feedback, and have a wonderful day. Bye.